Hello and welcome. In the last video we considered losses of energy in pipelines, and um, we considered for sudden expansion, and today we are going to be taking an example on that. A pipe increases suddenly in diameter from 0.5 meter to 1 meter. Let me draw that. A mercury U-tube has one leg connected just upstream of the change, and the other leg connects the larger section a short distance downstream. If there is a difference of 35 mm in the mercury levels, the rest of the gauge being filled with water, find the discharge. So what this basically means is that the pressure in this section is measured, and the pressure in this section is like the relative pressure in both sections are measured by mercury U-tube device, and the difference is 35 mm. So now to convert that into something that we know, difference of head, we can just say that will be equal to 0.035, which is 35 over 1000, into bracket 13.6 minus 1, that is P2 minus P1 over W, because this acts as the difference of air, the difference in pressure between these 2 points. So if we have P1 here and we have P2 here, the difference in pressure over the specific weight will be given as this, and our answer will be 0.442 meter of water. So what did they ask us to find? They asked us to find the discharge. So basically, if we have the fluid traveling, there will be a certain pressure here, which is P1. There will be a certain area, which is A1, and velocity, which is V1. And in the section 2 too, we will have pressure P2, A2 as the area, and then V2 as the velocity. So having that in mind, now we have to calculate the discharge. Normally discharge Q is equal to what? A1 V1, which is also equal to A2 V2. We can express this in full, where we have area, because the cross section is circular, area will be equal to 1 over 4 pi d square. Yes, 1 over 4 pi d square. So basically we can have it like this: 1 over 4 pi d1 square v1 is equal to, this is q, or let's remove the q first. Let us just equate a1 v1 and a2 v2. 1 over 4 pi d2 square v2. So we see that some things are common in both sides, but firstly let us know, what do we know and what do we not know? We know our d1 and we know d2, but we do not know v1, neither do we know v2, so we cannot just calculate the discharge straight up. So we first have to find v1 or v2 to calculate the discharge. Here we see that some things are common. Things like 1 over 4 are common to both sides, so we can cancel that out. 1 over 4 cancels 1 over 4. Pi 2 is common to both sides. Pi cancel pi. So basically what we have now is d1 v1 is equal to d1 square, is equal to d2 square v2. And so now we can get v1 in terms of v2. So basically v1 will be equal to d2 over d1 all square v2. So let's just put that in mind, and then let us see what can we do again here. Okay, we can apply Bernoulli's theorem between point 1 and point 2. So if we apply Bernoulli's theorem between point 1 and point 2, we will have something like this: P1 over W plus V1 square all over 2G is equal to the energy at the second area here, P2 over W plus V2 square over 2G, then plus the head loss, which is HL. But we got HL in the former slide. For this kind of condition, HL is equal to V1 minus V2 all square over 2G. So we can just substitute that in to HL, and that will give us V1 minus V2 over 2G. Then this is square. So we know P2 minus P1 over W already. So why don't we make that the subject of the formula? And basically we have P2 minus P1 over W is equal to collecting like times now, bringing P2 over to this side and then bringing V1 over to this side. And then we have V1 square minus V2 square over 2G minus V1 minus V2 all square over 2G. And then we can simplify this further. P2 minus P1 over W will be equal to V1 square minus V2 square minus into bracket V1 square plus minus minus 2V1 V2 plus V2 square. I've opened the brackets, then that will be over 2G. So basically that will become P2 minus P1 over W will now be equal to V1 square minus V2 square minus V1 square minus 2V1 V2 plus that will be minus V2 square all over 2G. So here we can see that V1 square, we cancel out V1 square, and then we can add minus V2 square and minus V2 square to give us minus 2V2 square, and that will give us, we are supposed to have plus here, correct that. So let me see if I can write it in this small space: 2V1 V2 minus 2V2 square over 2G, and we can still simplify this further to get 2V2 into bracket V1 minus V2 over 2G. And when we have this equation like this, we know V1 in terms of V2. So but here we can solve this further. We can get, because we know D2 and we know D1, we can just input those values. V1 will now be equal to 1 over 0.5 all square times V2. So basically V1 is equal to 2 square times V2, which is equal to 4V2. So we can now substitute in this equation V1 is equal to 4V2. So anywhere we see V1, we substitute 4V2. So basically P2 minus P1 over W, and write equal to 2V2 into bracket 4V2 minus V2 over 2G. So 2 can cancel 2. We now have, this will now be 3V2 times V2 over G, and that will be equal to 3V2 square over G. Now let us input our value for P2 minus P1 over W, which is equal to 0.442 will now be equal to 3V2 square over 9.81. So now making V2 square the subject of the formula, we have V2 square will now be equal to 0.442 times 9.81 over 3. V2 square will be equal to, imputing this on my calculator now, I have 1.4453, and finally we have V2 to be equal to, that will now be square root of that value, 1.202. But don't forget, what we want to calculate is discharge. Q will now be equal to A to V2. Now that we know V2 and we know the diameter of the section 2, we can easily find our discharge Q. So Q will be equal to 1 over 4 pi D2 square multiplied by V2. So Q will now be equal to 1 over 4 pi, then multiplied by D2 square, which is 1 square, multiplied by V2, 1.202, and the answer to this, Q, will now be equal to 0.943 meter cubed per second. This is the answer to this example. Before we finish this section of sudden expansion, there is a special case in the case of sudden expansion. Now, when a pipe discharges into a large reservoir, such as the one shown in the figure 2, through a sharp exit, the conditions are equivalent to sudden enlargement, but in this case, V1 is equal to the pipe velocity, which is equal to V, that is the pipe velocity V, and V2 is equal to the reservoir velocity, which is usually equal to 0. So for the formula, our formula for head loss is normally V2 minus V1 square over V2 minus V1 square over 2G. So if we substitute that into this now, we get V2 is 0 minus V square over 2G, which will give us V square over 2G. So for head loss, when a pipe is discharging into a large reservoir, it is V square over 2G. Now, thank you for watching this video. Like and subscribe this channel, and we would love to hear from you. Comment in the comment section below. I am Olunlade Joshua. Thank you. God bless you. Bye.